Hey, what's up, Logic fans? It's Ash again. Today we do our last section on 5.9, our last section in Chapter 5, so Section 5.9, the ninth section on quantificational semantics, the limits of quantificational semantics. I'm really excited to talk about this with you today because we get to discuss, both the limits and some of the more general results about quantificational semantics to help round out your study of the subject. So let's rock. Okay, so in this section we're going to be talking about the limits of quantificational semantics, and that's going to include some things about, what can and cannot be demonstrated about, in particular, invalidity, okay, which has been our primary focus through the chapter, how to demonstrate invalidity using tableau techniques. Now, in order to make some of these more general points and introduce you to some higher level concepts in logic and quantificational semantics, what I want to do is walk you through a string of arguments that will build us up into some of these higher level points, and I think that that's the best way to make all of the ideas salient. So let's start with this one. Okay, here's an argument. This argument is invalid, okay, and you can demonstrate it to be invalid with an interpretation that has any number of objects in it. So, for example, with a 3-object interpretation, you could have A, B, and C all have F and none of them have G, and then you would have demonstrated the argument to be invalid. Okay, that would be a 3-object example. My question for you is, what's the fewest amount of objects required to demonstrate this argument invalid? It's a bit of a trick question. So think about it for a second and pause now. Okay, hopefully you've had a chance to think about this, but the fewest amount of objects required to demonstrate this argument invalid is 0. Okay, none. So picture an empty domain. Okay, now on an empty domain, what happens to this sentence? Well, it turns out to be true. This is something we had occasion to discuss in Chapter 4 when we discussed vacuous truth, okay? But this would be vacuously true on a domain with no objects, okay? So refer back to Chapter 4 if you want to figure out why that is. Of course, the statement also discussed in Chapter 4 that at least one thing has the property G is false if there are no objects. So we've got, on a no-object interpretation, a true premise and a false conclusion, and therefore that demonstrates this argument to be invalid. And of course, it's also the fewest amount, right? Because you can't have less than 0 things. So this argument is invalid. You can demonstrate it to be invalid in the way we've been doing for a while now, since at least 5.5. Okay, just by providing an interpretation. But now we're asking a slightly more general question, which is, what's the fewest amount of objects necessary to demonstrate the argument invalid? And in this particular case, the answer is 0. So what I want to do is collect this result over here on a separate page where we can keep track of our initial results. So we looked at this argument, it was invalid. The fewest amount of objects required to demonstrate that it is semantically invalid was 0. Okay. All right, let's continue our progression. Next argument. Here's a new one. In some ways, I've just sort of reversed the premise and the conclusion, but new argument. Same question. What's the fewest amount of objects required to demonstrate that this particular argument is invalid? Pause now. Okay, hopefully you've had a chance to think about it. The fewest amount of objects required to demonstrate this argument invalid is 1. Obviously, you cannot demonstrate this argument to be invalid with 0 objects. A 0-object interpretation will make the first premise false. And in order to demonstrate invalidity, you need the first premise to be true. Okay, so then the question becomes, can I do it with 1 object? And the answer is yes, you can. If you let the 1 object, call it little a, have the property F, but lack the property G, then you will have done it. So it would look like this. So it would look like this, right, where we have A having the property F and lacking the property G. Then there's at least one, this is true, and this is false, right? And so the fewest amount of objects required, because again you can't do it with 0, is 1 for this particular argument. Okay, let's collect that result on our page. So the fewest amount of objects required to demonstrate this argument invalid was none. Could be done with none. The fewest amount of objects required to demonstrate this argument semantically invalid was 1. Okay, let's keep the progression rocking and really pay attention to how the progression builds here. All right, same question here. For this argument, what's the fewest amount of objects required to demonstrate that it is invalid? It is invalid. What's the fewest amount of objects required to demonstrate that? Pause now. Okay, so in this case, the fewest amount of objects required to demonstrate the argument invalid is 2. Okay, so let's go through that. Basically, in order to make the first premise true, we need an object, right? So notice how I've played with the knots here. Okay, so I'm going to use the object A to make the first premise true. At least one thing satisfies this description. It's not F1 and it's F2. Okay, and it'll become clear why I'm doing F sub 1 and F sub 2 shortly. Okay, so that object A makes the first premise true. Object B is going to make the second premise true, but notice, it's not the case that one object could do it based on the distribution of the properties here, having and lacking them. And then, of course, I need it to be false that everything is G. And so that's going to be a simple way to do that, is just to have at least one thing that lacks the property G. So here's an interpretation in 2 objects, right, that would demonstrate this argument to be invalid. Of course, you can't do it in fewer because you can't do it with 0, because a 0 object domain would make both the premises false. We need them both true. You can't do it with 1 object because of the way that properties are sort of distributed here. Okay. All right, so let's collect this particular result. So again, for this argument, it was no objects was the fewest amount to demonstrate invalidity. For this argument, it was 1 object that could demonstrate invalidity. That was the fewest amount. And for this argument, the fewest amount of objects required to demonstrate invalidity was 2 objects. All right, one more. Okay, try this one. What's the fewest amount of objects required to demonstrate that this invalid argument is in fact invalid? Notice the progression of the knots. Pause now. Okay, so you've probably been able to figure out that the answer is 3, right? So the fewest amount of objects required to demonstrate this particular argument invalid is 3. You can't do it with 0, you can't do it with 1, you can't do it with 2, but you can do it with 3, okay? And notice, the object A here makes the first premise true because it lacks F1 but has F2 and F3. The object B makes the second premise true by having F1 and F3 but lacking F2, and the object C makes the third premise true by having F1 and F2 and lacking F3. And then, of course, we can guarantee that the conclusion is false just by having a not on one of them. We'll put it on object A for the property G, and so it's not true that everything has the property G. And so we've got this really, really nice sort of progression here where we can see that some arguments can be demonstrated invalid with a certain amount of objects, but no fewer than that certain amount of objects. Okay, that's the big picture idea here. So let's collect this result onto our page here of results. Okay, so here's all of our arguments all sort of lined up. They're all invalid. You can demonstrate this one, with the fewest amount of objects possible is none, then 1, then 2, then 3, and you can kind of see the progression of how this is going. So if I created a one with a fourth premise, right, that required 4 objects to demonstrate that it was invalid, you would need a D, you would need an F4 column, and then the minuses are getting carried out here, and you can extrapolate the pattern for how to carry this task out, and hopefully you can see that and appreciate that it's true. Okay, so this idea of the progression leads us to the first theorem of 5.9, our first sort of larger idea of quantificational semantics, okay? And I'm going to present it this way. So first let's read it through and then I'm going to explain it. If this is true, then this is true. Okay, so it's an if-then statement. If an argument is demonstrably semantically invalid with n objects, okay, suppose it's like 16. If you can demonstrate that an argument is semantically invalid with n objects. So here we demonstrated it with 3, right? Then it is demonstrably semantically invalid on some interpretation with n plus 1 objects. So this argument would therefore be semantically demonstrably invalid with 4. Or if n was 16, then there would be some interpretation with 17 objects according to which that same argument is invalid. Okay, now this theorem does not say that, okay, if an argument is demonstrably semantically invalid with n objects, then it is demonstrably semantically invalid on every interpretation with n plus 1 objects. So this one is demonstrably semantically invalid with 3 objects, and according to theorem 5.9.1, it is therefore demonstrably semantically invalid on some interpretation with 4 objects. Okay, some interpretation, not every, at least one. There's at least one tableau with 4 objects in 4 individual constants, okay, according to which this argument is invalid. At least one. There might only be one. It might be semantically invalid on all of them. Who knows, okay? At least one, not necessarily all, okay, is the point. And as we've noticed, you can ask yourself, does this work the opposite direction? Meaning, if an argument is demonstrably semantically invalid with, say, 3 objects, is it thereby demonstrably semantically invalid in some interpretation with n minus 1, that is, say, 2 objects? And the answer is no. We saw here that this argument could be demonstrated semantically invalid with 3 objects, and that was the fewest amount. In other words, there's no interpretation in 2 objects that demonstrates this argument to be invalid. So it only works one direction, right? If you're demonstrably semantically invalid with n, then you're also demonstrably semantically invalid with n plus 1, but not necessarily n minus 1. It doesn't mean you're guaranteed to not be demonstrably semantically invalid with fewer, right? It's just guaranteeing that there is one interpretation with more objects according to which you're invalid. And then, this is sort of leaving alone the idea of what's the fewest amount, okay? It just doesn't guarantee it, is the point. Okay, so interestingly, and this is something you may have discussed with your instructor already, right? If you're presented with an argument, let's say like this one on an exam, and you're tasked with demonstrating that it is semantically invalid, so the professor's saying, here's an argument, it's invalid, demonstrate it. Give me a tableau interpretation where this conclusion is false and all the premises are true. You might not know how many objects you need to use. Okay, now typically your professor isn't going to require is not going to give you some argument that requires 15 is the fewest amount, okay? Typically it'll be around 3 or 4, but you can ask them about that for further instruction. But the point is that blindly looking at an argument, subject to some constraints we're going to talk about in these videos, just looking at an argument, you don't know. It may very well be invalid, and you're trying it with 1 object, you're trying it with 2 objects, and you just can't get it to work, and you're wondering why, and the professor told you it's invalid because it actually requires 3 is the fewest amount you can actually demonstrate that result. So blindly looking at an argument pulled out of a hat, okay, just at random, and now it's on your test page in front of you or your homework page in front of you, you actually don't know. Again, subject to some things we're going to discuss here, you generally speaking do not know what the fewest amount of objects is. Now, I set these ones up in a nice progressive way so that you would have an intuitive instinct about it, just to sort of make these wider theorems salient to you, okay? But generally speaking, looking at eyeballing an argument, you might not know what the fewest amount is. Okay. All right. We're a little pressed for time here, so I'm going to spill this into the next video, and we'll continue discussing this theorem along with some others. See you on 5.9b.